Welcome to the deep dive. Let's jump right into a pretty fascinating idea today. Imagine a world where, your clothes aren't just fabric, but they're actually generating power from your movement.
Right, like just walking around.
Exactly. Walking, cycling, maybe even just tapping your fingers while you're sitting at your desk. What if all that movement, that kinetic energy, could actually be captured and, well, used?
It sounds a bit sci-fi, doesn't it? But yeah, harnessing that ambient energy, the mechanical stuff your body produces all the time, that's really where some cutting-edge research is heading.
And that leads us straight into the topic for this deep dive. Harvesting energy from the human body, specifically using wearable textiles.
Yeah, and our main source today is a really interesting research article. It's called Textile-Based Triboelectric Nanogenerators Integrated with 2D Materials, and it was published in Ecomat.
So our mission really is to unpack what this paper found. We want to understand the tech they developed and explore what it could actually mean for the future of wearables, e-textiles.
And for you listening, this is about getting a handle on a potentially game-changing power source, something sustainable, wearable. It could really change how we power all those little smart devices we're starting to wear.
Okay, so let's set the stage. Why is this even needed? I mean, we've seen this huge boom in wearable tech, right? E-textiles.
Definitely. Sophisticated biosensors, smart health monitors, portable gadgets woven into fabrics. It's all tied into the Internet of Things, the IoT, growing so fast.
But all these things need power. And that's the snag, isn't it?
That's the big challenge. Our usual go-to, batteries, they have drawbacks for wearables. They're often rigid, can be kind of bulky, and they don't last forever or need recharging constantly.
Right. Try sewing a standard AA battery into your shirt. It just doesn't work. That stiffness, that bulk, it really limits how, truly wearable and comfortable these advanced e-textiles can actually be.
Exactly. So there's this really clear need for a power source that's sustainable, yes, but also fundamentally flexible, durable, and something you can genuinely build into the fabric itself.
And this is where the paper introduces Triboelectric Nanogenerators. TEs. Sounds complex.
The name's a mouthful, yeah. But the paper presents them as a really promising way to grab that mechanical energy vibrations, pressure, movement, and convert it into electricity.
How do they actually work? What's the basic idea?
Well, it hinges on something called the triboelectric effect. It's actually pretty common, like static electricity when you rub a balloon on your hair.
Okay.
So when two different kinds of materials touch, they can exchange electrons and end up with opposite charges. Then when you pull them apart, especially under some kind of mechanical force.
Like layers of fabric moving against each other as you walk?
Precisely. That separation of charged surfaces creates a voltage difference. And that voltage is electrical energy you could potentially capture, maybe run electronics directly, or charge up a small battery or capacitor.
Okay, that makes sense. And the paper specifically looks at textile-based tangs, T-tangs.
Right, because textiles are naturally lightweight, flexible, ideal for clothing. But the paper points out that historically these T-tangs had a bit of a limitation.
Which was?
Their power output. It tended to be quite low, maybe not enough for a lot of practical uses.
Gotcha. And this is where the new research comes in, trying to boost that performance.
Exactly. They focus specifically on integrating what are called 2D materials.
Okay, 2D materials. Graphene is the famous one, right? Super thin sheets.
Yeah, graphene's the poster child. Think materials that are incredibly thin, maybe just one or a few atoms thick. They have these really unique electrical and surface properties.
So how do these super thin materials help make the tangs better?
Well, the paper explains they can do a few things. They can act as really efficient electrodes to collect the charge. They can be buffer layers. But crucially, they can really enhance the overall performance, how much power you get out, and also improve the efficiency and, importantly, the durability of the whole tang structure.
But the paper mentions there was still a hurdle, even with early attempts using 2D materials.
Yeah, exactly. Some previous work had used 2D materials in wearable tangs, but things like long-term durability and stability were often still, not quite there. And there wasn't a huge focus specifically on textile-based tangs using these materials to create a fully self-powered system. That's the gap they aimed to fill.
Okay, so that brings us to the actual system developed in this paper, a high-performance, textile-based, self-powered system.
That's it. It's got two main parts. The energy harvester, which is the T-tang, and then an energy storage unit, a textile supercapacitor or T-supercap. And critically, both are built using textile-friendly materials.
Let's break down the T-tang first. The base is just regular cotton fabric.
Yep, standard cotton fabric is the substrate. Then they use graphene, that 2D material, for the electrodes. There's an insulator coating that acts as the positive tribo layer.
The material that tends to give up electrons.
Right. And then thin Kapton tape as the negative tribo layer, the one that tends to grab electrons. And importantly, a little sponge spacer in between.
What's the sponge for?
That allows for that crucial contact and separation. It lets the layers press together, then spring apart when the pressure is released. That movement is what generates the power.
And the key innovation here, the real booster shot, was adding another 2D material, MOS2.
Exactly, molybdenum disulfide. The explicit goal was to push the T-Tang's output higher by using both graphene for its great conductivity as electrodes, and this OS2 to really enhance the triboelectric effect and the interaction between the layers.
And it works in that contact separation mode. Press, release, press, release.
Yeah. Every time you press, you get a voltage peak, maybe positive. When you release, you get another peak, maybe negative. It's this constant cycling from movement that generates the usable electricity.
Okay, now for the results. They did a lot of optimization, right? Testing different amounts of this MOS2 stuff.
They did, and they found it made a big difference. Integrating the MOS2 significantly boosted the performance. After trying various concentrations, they landed on 0.5 grams per liter as the sweet spot for the highest output.
And how much better was it?
The numbers are pretty striking. With that optimal MOS2 concentration, they saw about a 35% improvement in performance compared to a similar T-Tang that only used the graphene electrodes.
Wow, okay, so that MOS2 really adds something significant.
It really does. They also interestingly found that putting the MOS2 composite gel on just one of the contacting surfaces worked better than putting it on both.
Huh. Why is that?
They suggest that if both surfaces become too similar in composition because of the MOS2, it might actually weaken the charge separation, the electric field between them, so having that difference was key.
And the peak performance numbers they hit with this optimized design, they sound pretty wild for something made with fabric. Over 1,000 volts.
Yeah, a record-high open-circuit voltage VOC of 10 and 68 volts.
Yeah.
And a power density of 14.64 watts per square meter under a force of about 22 newtons, which is, a firm press.
And they mentioned this as a record.
They specifically state it's the highest reported value among cotton fabric-based tents published so far. Now, obviously, most tiny sensors don't need 1,000 volts.
Right.
But achieving that kind of voltage level shows the potential power density. It means you could potentially charge up storage, like that supercapacitor, really quickly, or maybe power a whole array of small devices at once.
They also tweaked the physical structure too, didn't they? Like the thickness of the layers.
Yes, they found optimal thicknesses for the insulator coating, around 570 micrometers, and for that sponge spacer, about 5.5 millimeters, to get the best output. And they confirmed, as you expect, that if you make the active area bigger, you get proportionally more power.
Okay, performance is one thing, but for clothes, it has to be durable and flexible. How did it hold up?
This is where it gets really compelling for wearables. They tested the endurance pretty thoroughly. It maintained steady performance with almost no drop over 1,000 cycles of pressing and releasing under a decent force.
1,000 cycles is a good start. And flexibility. Can it handle being bent like clothes are?
Apparently, yes. They reported it kept an amazing 96% of its electrical output, even after being bent 100 times around a tight curve, an 8-millimeter radius. That's like folding it pretty sharply around something like a pencil.
That's really impressive. It suggests it could actually survive being worn.
It really does. And they also tested how it responded to different forces and frequencies. The output voltage went up significantly with more force, hitting over 870 volts at 22 newtons. And it also increased slightly with faster frequencies, up to about 8 hertz, which is relevant for capturing energy from quicker movements like running or cycling.
Now, the paper was also honest about longer drum testing, right? It wasn't perfect forever.
No, and that's good science. They noted that during extended testing, especially after the first month or so, they did see some decline in performance.
Any idea why?
They suggested a few factors. Maybe some residue building up from the Kapton tape over time, possibly tiny surface cracks forming from all the bending and stress, and also environmental factors like humidity could affect the charge density on the surfaces.
Okay, but it didn't just die completely.
No, and that's the crucial part. The decline actually slowed down over time. And even after 7 months of continuous operation, the device still retained about 45% of its peak output, which honestly, for an early-stage textile device like this, is still pretty remarkable long-term stability.
Right, so they've got this really quite efficient T-Tang harvesting energy from movement, but you can't always use the energy the instant it's generated. You need storage.
Exactly. And that brings us to the second piece of their system, the textile-based supercapacitor, the T-supercap. That's the energy storage part.
Its job is basically to act like a little rechargeable battery, but one made of fabric, collecting the energy from the T-tang.
Pretty much. It smooths out the power delivery, so electronics can run continuously, even if the movement generating the power stops for a moment.
And how did they build this T-supercap? Also using textiles.
Yes, designed right onto textile. They used an in-plane symmetrical design, again using graphene for the electrodes, it's good for storage too, and a flexible PVA gel electrolyte. They also showed how you can connect several of these in series to get higher voltage storage. They demonstrated 3 connected together, for example.
And did it work well? Did it store energy effectively and last?
Yeah, the performance looked good. It behaved electrically much like an ideal double-layer supercapacitor, which is known for fast charging and discharging. It was also very flexible. They bent it into various shapes, and it kept working. And durability was excellent again, retaining over 95–96% of its capacitance after 1,000 charge-discharge cycles.
Wow.
And when they connected 3 in series, they behaved as expected, reaching about 3 volts in roughly the same time it took a single one to reach 1 volt. So it scales properly.
Okay, so we have the fabric energy harvester, the T10, and the fabric energy storage, the T-supercap.
Yeah.
The big question is, what happened when they put them together? Could it actually do anything useful?
That's the proof of concept, right? And yes, they show the integrated system charging up those textile supercapacitors, just using hand tapping, applying moderate force, maybe 7 to 10 newtons, at a rate of 4 to 6 taps per second.
Like drumming your fingers.
Kind of like that, yeah.
Yeah.
They managed to charge 9 of their T-supercaps connected in series up to 10 volts in about 250 seconds.
That actually sounds quite practical for harvesting energy from everyday fidgeting or movement.
It does. And they also showed it could charge up standard commercial capacitors very quickly, like a 1 microfarad one, up to 10 volts in only about 6 seconds. That versatility is important.
So did they power anything real with it?
Yes. They demonstrated several really cool real-time applications.
Like what? Give us the highlights.
Okay, so they integrated the T-tang into a sock. And just for the pressure of walking, it functioned as a self-powered step counter sensor. No external battery needed.
That's neat. What about powering lights? Always a good visual demo.
Absolutely. They showed it lighting up a surprising number of commercial LEDs. With hand tapping, they powered over 200 LEDs simultaneously.
200? Wow.
Yeah. While cycling or walking, combined with some extra tapping, over 160 LEDs. And maybe most impressively, just by walking normally with the T-tang fixed inside socks, it could power over 120 LEDs.
Okay, that really shows it generating significant power just from natural walking motion.
Definitely. They measured the open circuit voltage just from walking with it in the sock at around 480 volts.
Still a very high voltage.
Yep. And they also, as mentioned in the abstract, showed it powering a miniature watch, demonstrating its potential for small, common electronic devices.
So let's try and wrap this up. What's the big picture takeaway from this research?
Well, the core achievement, I think, is developing this highly efficient textile-based ting, showing that integrating these 2D materials, the graphene and especially the MOS2, can really push the performance significantly.
And then pairing it with the fabric supercapacitor.
Exactly. By combining the harvester with that durable, flexible, textile supercapacitor, they've created a genuinely robust, self-powered system, all using materials compatible with clothing.
It really feels like it lays down a strong foundation, doesn't it, for the next wave of wearable e-textiles?
I think so. It's a significant step towards that goal of sustainable, autonomous power sources that are just seamlessly part of what we wear, getting us closer to a future where maybe the energy for your earbuds or your fitness tracker comes just from you moving around.
So thinking about this from the perspective of you, the listener, what could this actually mean? We're seeing more and more tiny computers, sensors, communication chips getting integrated into clothing. Could this kind of tech mean your next smart jacket actually powers your health monitor all day long? Or maybe your running shoes track your pace and charge your phone just from your run?
It really opens up possibilities. And given the high voltage they achieved and that impressive durability, especially when embedded in something as simple as a sock, it makes you wonder, what other everyday personal power needs could this kind of fabric-based energy harvesting fundamentally change? Could our clothes become our personal power plants?
That is a really provocative thought to end on. This deep dive really highlights the incredible potential hiding in just moving, energy woven right into the fabric of our lives.
It certainly seems that way. A sustainable, flexible, high-performance power source that could be as simple as putting on your socks. Pretty amazing stuff.
Thanks for joining us for this deep dive.